Okay, so this is a quick review over calculus topics. So let's say we have a position time graph and it has some kind of strange function like this. And I want to figure out the velocity time graph. Well, in order to do that, I would have to draw a tangent line everywhere along here to figure out what that slope is, and that slope would be the instantaneous velocity, and I could plot that. And when I do that, I see that the equation that I get for the velocity time graph is related to the position time graph equation in a very systematic way. And it would be equal to, if it was a t to the n power, it ends up becoming t to the 1 less power. But if I decrease the power, then I have to increase the coefficient by multiplying by the bigger power, in this case n. And then I could go ahead and do that same thing for the velocity time graph. I can find the slope of the velocity time graph, and that would give me the acceleration time graph. But again, that's related to the velocity time graph equation in the same way that the velocity time graph equation was related to the position time graph equation through this thing called a derivative. So now the power of the t is going to be 1 less than it is now, so it's going to be n minus 2. And I would be multiplying the coefficient by the bigger power, in this case n minus 1. And so that's how you find the derivative. Realize finding the derivative is really just finding the slope. So here are some really simple rules for figuring out what the derivative would be. And again, this is whenever you're trying to find the slope. And this is for what's called the power rule. It works for most functions. You decrease the power by 1, and then you have to increase the coefficient by multiplying the coefficient by the larger power. And that was the original power usually. So it's kind of a nice yin and yang here. You decrease the power by 1, but you have to increase. So decrease power by 1, but increase the coefficient by multiplying the coefficient by the larger power. Now there are a couple exceptions to this, or 4 exceptions. Really in E and M, the only 2 that are really important for us are natural log and e to the t. You might come across sine of t and cosine of t, but mostly these are the important ones right here. So if I want to figure out what the derivative, the slope of a natural log graph would be, that's just simply going to be 1 over t. So dx dt is 1 over t. It's one of those you have to kind of memorize. And if I want to figure out what the slope of an exponential graph, e to the t, is, well, that one's even easier to memorize. dx dt is just simply equal to e to the t. And as I said, the sine and cosine come up less frequently in E and M, but it's probably good ones you should memorize too. The derivative of sine of t is cosine of t. So again, we're talking the slope. If you had a sine of t graph and you just try to draw tangent lines everywhere along there and found the slope, you'd end up getting, and then plotting it, you'd end up getting cosine t. If you have a cosine graph, and again you find the slope everywhere along there, you end up getting negative sine of t. So those are the only 4 exceptions to this rule up here, this really nice simple rule. Now, sometimes we have to expand upon this a little bit, and it's using what's called the chain rule, but it really isn't that much more difficult. So notice there's a 2 here, so I have 2t, and here I have negative 2t, and here I have sine of 2t and cosine of 2t, whereas before it was just t in every one of these. Well, in that case, not only do I have to take the derivative natural log of 2t, I also have to then take that answer and multiply it by the derivative of 2t. Same thing here. I have to take the derivative of e to the negative 2t, but then I have to multiply it by the derivative of negative 2t. Same thing here and same thing here. Alright, so you can see the derivative of natural log of 2t is 1 over 2t, but then the derivative of 2t is 2. Multiply them and I get 1 over t. Same thing here. Derivative of e to the negative 2t is e to the negative 2t, but then the derivative of negative 2t is negative 2. So I get negative 2 e to the negative 2t. the derivative of sine of 2t is going to be cosine of 2t, but then the derivative of 2t is 2. Multiply it, I get 2 cosine 2t. And then for the last one, derivative of cosine of 2t is negative sine of 2t, but then the derivative of 2t is 2. Multiply it, I get negative 2 sine 2t. Now, there are some more complex ones I did put on here, but it's similar. For instance, what if you had something like x equals cosine t times sine of t? Well, then you take the derivative of the first times the second plus the derivative of the second times the first. So it's not much more difficult than that. And these, by the way, these don't come up a whole lot. I mean, the ones that I have right here are probably, especially the natural log and e to the 2t, are probably the most important ones for E and M. Okay, so now what I want to look at is rules for figuring out the area. This is called integration or anti-differentiation. So let's say we have an acceleration time graph, and I want to figure out the velocity time graph or the position time graph. For this one, if you remember last year or a couple years ago, we would find the area underneath this graph. Well, that's called integrating or antiderivative. And the symbol that we use for this in calculus kind of looks like a summation. So I'm summing up all the area. And this dt just says I'm summing it up with respect to the t variable. So I'm taking the area, or excuse me, I'm taking the acceleration times dt, which is a little tiny width. So imagine breaking this up into lots of little rectangles. They all have width of dt, and then have a height of a. So I'm taking the height times the width. That gives me an area, and now I'm adding them all up. So this was the equation I had before for acceleration, and now for the velocity time graph, this is now the new equation. So notice the power increased by 1. So if I add 1 to n minus 2, I get n minus 1. So it increased. Well, if I increase the power, I'm going to have to do that yin-yang thing and kind of decrease the exponent by dividing by the bigger power. So n minus 1. That's why the n minus 1's canceled, and I have n here. Let's take it a step further. Now I find the area of the velocity time graph to give me the change in position. And again, this would be the symbol for integration, finding the area. I'm taking all those velocities, the heights, times the width of the rectangle. So the width would be dt, the height would be v. Find an area, and then I add all those little tiny rectangles up. That's what the little s there means, summation. And that gives me the position, or actually the change of position. So again, notice what happened to the power. It increased by 1, so it went from n minus 1 to n. So I increased the power by 1, but I have to decrease the coefficient by the bigger power. So I would divide this old coefficient by the bigger power, which is n, and I get a. So I'm not sure why that's not showing there. That should be a summation there. Summation dx equals summation n at n to a t to the n minus 1 times dt. And when I do that, on the left hand side I just simply get x of t. On the right hand side, notice the power becomes 1 bigger, and I take that bigger power, which is n, and I divide the coefficient by that bigger power, n. So n a over n would just be a. So these are the simple rules for integration. You increase the power by 1 and decrease the coefficient by dividing the coefficient by the larger power. Again, there are some exceptions, and these are related to the exceptions we already learned. If I have 1 over t, that's t to the negative 1 power. If I want to integrate that, it becomes summation dx equals summation or integral sine of 1 over t dt. Well, that's going to be natural log of t. For this one, notice I multiplied the dt to the other side. Take the integration of dx, gives me x. Integration of e to the t dt gives me e to the t. I multiply both sides by dt. Now I integrate, so integral of dx gives me x. Integral of cosine t dt gives me sine t. And the last one, I multiply both sides by dt. Integral of dx gives me x, and integral of negative sine of t dt gives me cosine of t. So those are kind of the exceptions. The most important ones for E and M is the first two, natural log of t and e to the t. So let's look at a couple applications from E and M. So let's say we have a potential, a voltage, that's dependent upon its position in space, and it's given by 3x to the fourth. And we want to find the E field in that region of space. Now we know that the E field is related to the voltage as the negative derivative of the voltage. So if I find the derivative of this, that means the power decreases by 1, so x to the third. And it's going to be, if you decrease the power, you got to increase the coefficient. So I'm going to multiply 3 times the bigger power, which is 4. 4 is bigger than 3. So I get 12. The only problem with E and M is in E and M we have this negative symbol, so I have to put a negative there. So negative 12x cubed. That's the answer. Okay, let's look at a more recent one dealing with integration. So let's say we have a cylinder or something, and we have the E field is given as Q over 2 length times pi over epsilon naught r. And we want to find the change in voltage with respect to r, the distance away from the cylinder. We know the change in voltage would be equal to negative integral of E r dr. So I'm going to integrate that, and all of this part comes out front. And so that would just simply be negative Q over 2L pi epsilon naught, but then 1 over r, I integrate that and I get natural log of r. Now, some of the more complex stuff you have to put in limits of integration. So let's say we have a point charge, and we're going to start at infinity, and we're going to move toward the point charge all the way to 2.1 meters. And I want to figure out what the change in voltage is from infinity to 2.1. Well, that would be equal to this integral, the integration from infinity to 2.1 of q over 4 pi epsilon naught r squared dr. So when I integrate this, the q over 4 pi epsilon naught, that's a constant that can come out front. And so really I'm integrating dr over r squared from infinity to 2.1. And so when I do that, this would be r to the negative 2 power. That power will increase to r to the negative 1 power. But I have to decrease the coefficient by dividing by that bigger power of negative 1. So there's a negative 1 out front. That negative cancels this negative, and so I get a positive q over 4 pi epsilon naught. I plug in 2.1 and infinity for the r, because remember it was 1 over r, and I have the quantity 1 over 2.1 minus 1 over infinity, and that simplifies to that. That's the final answer.